We have been talking a lot about the phase relationship between V and I. So let's say for pure R circuit, the V and I are in phase. For pure C, V lags I by pi over 2. For pure L circuit, V leads I by pi over 2. So I think you can see that I've placed a lot of importance on this really phase relationship. And why do I do so is because the phase relationship between V and I actually dictates the behavior of the AC circuit itself. Because it's not just pure R, pure C, and pure L in the future. It can be a combination of R, C, and L. Okay, so it's important for us to be able to illustrate the phase relationship between V and I very clearly. So there's a few ways of doing so. The first way is the way that we are most used to, is to draw the sinusoidal curve of I and V. So you see here, we draw the sinusoidal curve for I, we draw the sinusoidal curve for V, and for this case, we can see clearly that it's in phase. For this case, you can see that they are out of phase, in this case by 90 degrees. In this case, you can see that they are out of phase also by 90 degrees. Okay, it's okay for us to express the phase relationship this way, but there's a flaw to this method actually. For this case, pure R is 0 degree, it's easy to see that they are in phase. If for pure C and pure L is 90 degree, it's still relatively easy for us to determine that the phase relationship is 90 degrees, seeing that there's peak here, then there's 0 here. There's peak here, there's 0 here. So it's still relatively easy to determine that this is 90 degree phase difference. But what if the phase difference is 10 degree, 30 degree, or even 60, 75, 4 degree? So when you enter these kind of numbers, right, it will be really difficult for us to really express the phase relationship through this kind of sinusoidal graph. So we need some kind of a better method for us to express the phase relationship clearly. And that's where phasor diagram comes in. So how does a phasor diagram works? A phasor diagram basically translates these two sinusoidal curves into an arrow, a vector, which we call it as a phasor. So phasor, it's the name for a rotating vector. So how does this rotating vector replace this whole sinusoidal graph over here? So we have a vector, and this vector phasor here, we call it I naught. So I naught here is a phasor, and this phasor, since phasor is a rotating vector, this phasor here will be rotating anti-clockwise with an angular speed of omega. Okay, you'll be rotating anti-clockwise with an angular speed of omega. So you see it move from this green arrow to this green dash arrow to this blue dash arrow, the purple dash arrow, the red dash arrow, the orange dash arrow, and the blue dash arrow. So in this case, it has rotated through an angle of 180 degrees after some time. Okay, so as the time increases, this phasor here will rotate anti-clockwise. So why does this phasor here has to rotate? So as you rotate to a certain angle and you obtain the projection of this vector here to the y-axis. Projection means by you project it to the y-axis, like project like this to the y-axis. You see that the value of this y component here will be equivalent to the instantaneous current, to the current at that specific moment. Okay, let's be more specific and pick time t2 here. Okay, so let's say at time t2, this phasor I naught here has rotated until it reached this angle, which I represent with the blue arrow here, the blue phasor here. So when you reach this angle over here and you try to obtain the y component of this phasor, you see that this y component of this phasor is basically just the instantaneous current at time t2. The phasor has rotated through an angle of omega t2, and the y component of this phasor here will be the instantaneous current at time t2. So it's the same thing for t3, 4, 5, and 6. So when you reach different angles, you put it, you do a y component, and that y component will represent the instantaneous current at that specific moment. Okay, so why is it true if you think about it, this arrow here, this phasor here does not change length. The length here should always be I naught. So if you trace out the arrow head, you should trace out a circle. Okay, so let's say we come back to this omega t to this angle, omega t to this angle. You see that in order to find the y component, you have to take the length of this thing, which is I naught, and multiply it with sine omega t. Sine omega t is the angle over here. So if you want to find the y component, you should take the length I naught times sine, because you want y component sine omega t. So if you are doing it I naught sine omega t, well, that's just I naught sine omega t. And you see that that translates into the instantaneous current at time t. Okay, that's why just by drawing one single arrow here, you are able to represent the whole sinusoidal curve, because you know that this phasor here will rotate with time. And of course, if you are drawing this phasor diagram, you don't need to draw these many arrows over here. You just need to draw the phasor at a specific moment. In this case, I choose to draw the phasor I naught when the time is equal to 0, where it starts at the in between 4th quadrant and 1st quadrant. Start at 0 degree. Usually we do maths here at 0 degree, right? So we start here, then time will be 0 here. Of course, you can choose to draw your phasor I naught over here. You can choose to draw it here. You can choose to draw it here, anywhere you want. But I pick this position because this is the position where time is equals to 0. So why do we need phasor diagram? We said just now phasor diagram is a better representation of the sinusoidal curve. So why do we really need it? It's because we use it to illustrate the phase relationship between two sinusoidal curves. It can be the sinusoidal curve between V and I, which is how we use this phasor diagram in this chapter. The phasor diagram here is to illustrate the phase relationship between the sinusoidal curve V and the sinusoidal curve I. Okay, so the key point here is not where I is pointing, whether it's 45 degree from the 45 degree or 90 degree or 135 degree. The angle of I or the angle of V is not the main point. The main point of drawing a phasor diagram is to see which is leading which and what is the angle between I naught and V naught. That's the main thing, because you want to investigate the phase relationship. Okay, so let's say for this first case that I draw over here, you see that I naught is having a greater angle compared to V naught. So you can think of it as I naught and V naught are both rotating anti-clockwise, but the phasor I naught here is leading leading V naught. Okay, I naught is leading V naught in this race where they are turning and counterclockwise. So in this case, we can say that I naught is leading V naught, or you can say that V naught is lagging behind I naught. So in this case, I say V lags I. So if you see here, the rotation should be positive. If you are turning this anti-clockwise, it should be positive. And you see that the phase angle phi here is going in the opposite direction. Okay, the phase angle must go from I to V, because phase angle is describing the angle of V naught with respect to I naught. Okay, it's looking for the position of V naught with respect to the I naught. So you should start from I naught, go towards V naught. So you see here, the phase angle is in the opposite direction to how we naturally rotate. So in this case, the phase angle should be negative. Okay, so you see that if it's lagging, of course V naught should be behind. And since V naught is behind, the phi should be negative because it's in the opposite direction to how you usually rotate. Let's look at the second diagram over here. If you look at the second diagram here, I've drawn my I over here, but my V naught here is actually leading the race because you are rotating this direction. You see that V naught is actually leading I naught in the rotation. So in this case, we see that V leads I because V naught is leading I naught. And if you look for the angle between I naught and V naught, you see that from I naught to V naught, this angle here is in the natural direction, which is anti-clockwise. So in this case, this phase angle here will be positive. So if V is leading I, the phase angle will be positive. If V lags I, then the phase angle will be negative. Okay, and as you can see here, I'll draw my I naught here for this diagram, but I change my I naught to be here for this diagram. So the angle of where am I pointing, it's not the main point. The main point is what is leading what and what's the angle between them, whether it should be positive or negative. That's the main point that we want to investigate through a phasor diagram. In any case, you're wondering what phi am I talking about over here? This phi that I mentioned here is the phi that you see in the equation over here. Okay, in this case, our phi here is negative pi over 2. Our phi here is negative pi over 2, and that's the phi that you will determine from this phasor diagram. Again, for this case, our phi is pi over 2 positive, so you see that V is actually leading I. Just like what we have say here, leads, then the phi should be positive. So the phi here is what you see in the equation. So to close up our discussion about phasor diagram is a more effective tool for us to illustrate the phase relationship between V and I compared to this sinusoidal curve that we have drawn here.